Hello everyone, this is Jala Babu, my roll number is 25BQ5A0408 from ECE B section. Today we'll talk about MOSFET drain and transfer characteristics. Introduction to MOSFET technology. What is MOSFET? MOSFET is a metal oxide semiconductor field effect transistor. It is the most widely used semiconductor device in modern electronics. It acts as a voltage control switch, enabling precise control of current flow through the electric field modulation. MOSFET are fundamental building blocks in digital circuits, amplifiers, power electronics, and integrated circuits. Powering everything for smartphone to satellites. Basic operation principles. The MOSFET operates by applying voltage to the gate terminals, which creates an electric field that controls the conductivity of the channel between source and drain. Voltage control device with high input impedance, fast switching capabilities for digital applications, low power consumption in standard mode. Understanding MOSFET constructions. There is a three terminals: gate terminal, source terminal, drain terminal. Gate terminal controls the channel connectivity through capacitive coupling insulator from the channel by the oxide layer, creating high input impedance. Source terminal, the reference point where carriers enter the channel, typically grounded in common source configuration for signal amplification. Drain terminal, collector of carriers from the channel. The voltage between drain and source determines the operating region and current flow. Channel formation. Connectivity path from between source and drain voltage exceeds the threshold voltage. Drain characteristics fundamentals. Current voltage relationship. Drain characteristics represents the relationship between drain current ID and drain source voltage VDS for different gate sources voltages VGS. These VA curves are essential for determining operating points of circuit design, understanding device behavior in different regions, calculating power deception and efficiency selecting. Appropriate MOSFETs for applications. Cutoff the three regions: cutoff region, linear region, saturation region. VGS cutoff region is VGS. Linear region is VDS. MOSFET access voltage control resistor. Saturation is VDS. This is the MOSFET drain characteristics fundamentals. Linear region analysis. MOSFET behavior when VDS less than VGS. Physical behavior in the linear or tried region, the channel is uniformly formed across its entire length. The MOSFET behaves as a voltage-controlled resistors with the drain current increases proportional with drain source voltage. The channel resistance RDS on can be modulated by varying the gate voltage, making this region ideal for switching applications on analog multiplexers. Mathematical expressions. ID equal to V by L of VGS to VT into VDS to V square DS by 2, where N equal to electron mobility, Cox A equal to gate oxide, capacitance W by L equal to width to length ratio. Key applications: analog switches, transmission gates, and resistive loads where variables resistance is required for signal processing. Saturation region dynamics. Uh, channel pitch off. Here is the three applications. Channel pitch off, constant current, and amplification mode. Channel pitch off is at the drain, and the channel narrows and evenly pitch offs when VDS reaches. Constant current is the further increases in VDS does not significantly change ID, creating a current source behavior. Application mode. Ideal region for analog amplifiers due to high output resistance and voltage gain. Saturation current equation ID equal to 1 by T. 1 by cos by W by L VGS to VT square into 1 plus less than VDS. The factor 1 plus less than VDS accounts for channel length modulation, where less than is the channel length modulation parameter. This effect causes a slight increases in a drain current with VDS, creating a non-zero output conductance. Transfer characteristics overview. Drain current variations with gate source voltage. Transfer characteristics plot drain current ID as a function of a gate source voltage VGS while maintaining constant drain source voltage VDS. The relations is fundamental for understanding MOSFET transconductance and designing amplifier circuits. Cutoff region VGS less than VT. Cutoff active region VGS greater than VT. Transconductance GM. The slope of the trans characteristics represents transconductance, a critical parameter for amplifier gain. GM equal to 6 by D by 6 VGS equal to Cox W by L into VGS minus VT. Practical significance. Transfer characteristics by help designers determine threshold voltage accurately, calculate voltage gain in amplifiers, optimize biasing for linear operations, access device matching in different pairs. Thresh, threshold voltage concepts. Physical definition. Threshold voltage is the minimum gate source voltage required to create a conductive channel between source and drain and ending significant current flow. Inverse layer formation. When VGS exceeds VT, minority carriers accumulate at the oxide semiconductor interface, forming an inversion layer that has a conductive channel. Factors influencing threshold voltage. Oxide thickness. Thinner gate oxide reduces VT by increasing gate capacitance, but requires carefully control to prevent breakdown and reliability issues. Substrate doping. Higher substrate doping concentration increases VT due to strong depletion region body effect for the modules with source separate voltage. Gate material. Work function differences between gate and semiconductor affects VT. Modern process is metal gate for precise threshold control. This is the typical VT range and temperature. For standard CMOS process at room temperature, VT decreases with the increased temperature. Practical applications and circuit analysis. Applications are digital lossy circuits and power electronics. Amplification and RF and wireless. Digital lossy circuits MOSFET from the bias of CMOS logic gates providing low pass consumption and a high integration density. Complementary pairs of NMOS and PMOS devices create inverters, LAN or NOR gates for processor and memory. Power electronics. High power MOSFETs in linear region enable efficiently switching in DC to AC motors, motor dividers, and inverters. Low RDS minimize conduction losses or improve efficiency. Amplification, common source, common drain, and common gate configuration. Utilize saturation region operations for signal amplification in audio and RF and instrumentation application with a high input to impedance. RF and wireless. High frequency MOSFETs, RF amplifiers, mixers, and oscillator leverage for fast switching speeds and low statistics capacitance for 5G, Wi-Fi, and satellite communications. Design consider for circuit implementation. Biasing networks. Proper DC operating point selection using voltage dividers, current minus or active loads ensure stable operations across temperature and process variations. Thermal management. Power reception requires heat sink, thermal wise, and a careful layout to prevent junction temperature existing rating. Characteristic effect. Gain drain capacitance classes Miller effect, reducing bandwidth, layout optimization, and source degradation help mitigate these effects. Key takeaways under a future scope. Characteristics, understanding and emergence trends in MOSFET technology. Design fundamentals. Threshold voltage, transduction, and VA relationship are essential parameters for amplifier gain, switching speed, and power efficiency calculation in practical applications. Advanced material, high gate dielectrics, metal gates, and 2D materials like graphene and MOS, MOS promise enhanced performance, lower power consumption, and novel device fundamentals. Thank you. Thank you for giving this option.